In an adjacency list representation of an undirected simple graph G equal to V comma E, each edge UV has two adjacency list entries, V in the adjacency list of U and U in the adjacency list of V. These are called the twins of each other. A twin pointer is a pointer from an adjacency list entry to its twin. If number of edges equal to m and number of vertices equal to n and the memory size is not a constraint, what is the time complexity of the most efficient algorithm to set the twin pointer in each entry in each adjacency list? And 4 options have been given for the complexity. So this is a question from data structures regarding graph. Here they are saying that for a graph we are having an adjacency list representation. That means for each edge u and v, first of all each vertex will have its own adjacency list entries, and then for each edge u and v will be added in u's adjacency list as well as u will be added in v's adjacency list. Now these two entries will be denoting the same edge only, so this will be called twin pointers. So in addition to having v in u's adjacency list, we'll also have the address of the entry u in v's adjacency list as well. I'll repeat that. Suppose I have u. In u I need to add the entry v. Similarly in v's adjacency list I need to add the entry u, and on top of that in u I have added v plus I need to add the address of u entry in v's adjacency list as well, meaning the address of this entry also I will be adding here. Similarly the address of this entry I will be adding here as well. So that's what they were saying, the twin pointer from an adjacency list entry to its twin. So we need to have a pointer from this entry to this entry as well as this entry to this entry. Now let's try to answer the question. Let us say I have a graph like this. Okay, it has 5 vertices, so there will be 5 adjacency lists, 1, 2, 3 and 5 for each of the nodes here. Now let us say I am starting BFS traversal in this tree. So I will start from node 1 here. I will see that it has edges to node 2, so I will be adding 2 in one's adjacency list. At the same time I will be adding 1 in 2's adjacency list as well. Now just now I added these 2 nodes, right, which means I have the address of these 2 nodes ready right now itself. So I can just add a pointer to each other in each of the entries like this. Okay, and then I will continue with BFS. From 1 we reach 2, after that we will be seeing 3, which means that in 1 I will be adding the entry 3 as well as in 3's adjacency list I will add the entry 1. Now just now I added these 2 entries, so I have pointers to it. I have the address of these 2, so I can just easily add the pointers to each other right now itself. Okay, now once edges are complete, after that I will be visiting 2. Now 1 we already visited, so we won't be visiting it again. 2 has this edge 3, so in 2's adjacency list we will be adding 3 as well as in 3's adjacency list we will be adding 2. Now these 2 were added just now, so I will just add the pointer like this directly. So now you get the idea. I just do the BFS traversal and each time I am adding one node in adjacency list, I will be adding its twin also in its adjacency list, and then and there I will be adding the pointer only. So this has the same complexity as doing BFS traversal, plus adding the pointer here and adding the twin pointer etc. will take only O1 complexity. So this algorithm will have the same complexity as the complexity of BFS traversal. Now the complexity of BFS traversal is nothing but big of n plus m. So the answer will, for our answer the complexity will be big of n plus m. Now looking at options, that is options B, they are given in theta notation, which is the same thing. B is the answer.